Well, good morning, everybody.
Good morning.
You can hear me, it seems. Can you see me?
No, I cannot see you.
Is it better
yes.
now?
Now yes. Now yes.
Okay, thank you. So nice to have the opportunity. Good morning. And let us start with our today's job. So we will have a lecture broken into two parts due to two topics that are quite different. The first topic is from electromagnetics, while the second topic would be more common. It would be about optimization. And the reason I include a chapter on optimization is that when I asked you for your knowledge at the beginning, it seemed to me that it would require some new information. Now, what I shall do, I will start with the electromagnetics part, possibly smaller today, and I will talk about the method of moments. But in fact, it would be just a brief introduction because next two lectures will be given by Miroslav Čapek, my younger colleague, who is really an expert in the method of moments. So it would be better that he gives you the full knowledge and I will have only a short introduction now. Well, let's start with it. So, in fact, some time ago, I had one of my students on a short stay in Aachen with Professor Rolf Jansen, and he has been doing there some work, and suddenly he asked me by email at that time that he would need to characterize a transmission line he has never had seen before. They have been working on high-speed communication. I mean, that means some gigabit speed. And he had something that was composed of two ground lines and a circular line inside. So something that is quite similar to a three conductor coplanar waveguide or coplanar line, but with a wire inside. And this was very tiny. The wire was the bonding wires, so 30 micrometers in diameter. And what he needed to was to obtain the knowledge about impedance. The propagation constant is known. It's a TEM structure, so that the velocity of light is kept. That's not a problem, but the impedance is a problem due to reflections. So he needed to find out the impedance of such a line, and he could not find it anywhere. And at that moment, I just tried to do it somehow quickly. So my way of thinking was, okay, we have three conductors, and it would be quite difficult to find out the impedance. Those two are grounds, so in fact this is grounded, and this is the hot wire, the wire with the voltage against ground. So I would like to calculate it somehow. Well, there would be some possibilities using conformal mappings that would be long to elaborate for, and possibly with some approximations it could work. But I had another idea. What would happen if I substitute this kind of line by something else? What if I have only a set of conductors, just wires on the surface? So I would have a number of conductors on the surface, a set of needles, infinite long wires, and of course on the other conductor also and on the third one as well. And this must be equivalent to the structure as to the electromagnetic field if those wires are tiny enough and if the number of those wires is sufficient, then it would converge to the field that has been the original case.
I can see the equations.
Well, there are no equations. I have just... Sorry?
I can see it.
You...
Thank you.
Is this better now? Thank you very much. Yeah.
Great.
It was only a picture, not an equation. Okay, but thank you for pointing this out. So I would just substitute the surface by a set of wires. Was that much better or not? Well, I have an equation that tells me about the field that is invoked by a charge sitting on a thin wire. That's possibly the first lecture of electrostatics. If I have a charge, which would be mostly denoted by tau, which is coulomb per meter as to the unit. So if I have this charge sitting on a straight wire, I would have around it an electromagnetic field that could be expressed in the terms of flux density or electric field strength or potential. And the potential around such a conductor is given by minus tau over 2 pi epsilon, where epsilon is the permittivity, times logarithm of r plus a constant, of course, because a potential should have a constant, where r is the distance from the center of that wire. So if I would have somewhere a point, for example here, so the potential that is invoked by this wire in this place would be given by this equation. Simple, isn't it? Well, and we can choose the constant with which we also choose the place where the potential is 0. But anyway, this is quite simple. We have a cause charge that causes a result, which is the potential. So now if we knew the charges or charge densities on all of those conductors, we could add the potentials as the surrounding media is linear, there is the superposition principle working. We could just add those potentials invoked by all of those charges or wires, and we would have the resulting potential. Once you know the potential, you can calculate anything you want in electrostatics. So that's fine. That would be fine if we knew charge densities sitting on those wires. So let's put it into an equation. We would possibly have to number those wires, wire 1, 2, 3, 4, 5, 6, 7, blah, 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 blah. And then we would have an equation something like the potential phi, which would be a vector. So let's give this a potential. Phi 1 would be the potential of the first wire, number 1, 2, 3, and so we would have a vector of potentials of all the wires, and this must be given, well, that would be a superposition, so a sum of potentials invoked by the other wires and the wire itself. So we would have a term like minus 1 over 2 pi epsilon. And now there would be a matrix we will return back to the matrix, and then of course we would have tau 1 to tau m, and we would phi m, so let's have m wires. Now how will this matrix look like? Well, of course the wire has a charge, and this charge puts some potential or some part of the potential to the surface of that wire. How far is a surface of a wire from its center? That's the radius of the wire. So I choose some radius for the wire. Let's call it A. So we have wires of a radius A. And this would mean that here we would have logarithm of A, and that would be on the diagonal. Diagonal points would be logarithm A for all the rows and columns in the matrix. The diagonal would be logarithm A, and if I choose just wires of the same diameter, I would have the same term on the diagonal. What would be somewhere else? For example, what would be here? The second term. Well, in fact, there would be the piece of potential phi that is caused by the charge sitting on the second wire. Well, the equation is still the same, just the distance now is the distance between the wire 2 and wire 1. So the second term, I would put it there in black, would be logarithm R21. Where R21 is the distance between the second and first wire. And the rest of the matrix would be full of logarithms. In doing this, I have omitted the constant for the potential, which is here not important. I can choose it deliberately and it would not make any change to the result at the moment. So okay, I have a matrix. Nice. So now I know that I have something like phi, which is a vector, is given by a matrix times a vector of charges. This is a vector, this is a matrix, this is a vector, a column vector. Well, now this is very nice. I have just written a set of those equations into a big set, but it does not help me very much. But still I have one more condition that I have not used, and that is, if I want to solve this structure, mostly I would like to find out, for example, the capacity per meter of the line. So what I would do, if I measure that, well, I would take a special apparatus, connect the terminals to the structure, and it would first discharge the capacitor, then it would charge the capacitor with known charge up to a known voltage and divide voltage and charge to get capacity. So if I would like to calculate the capacity, I would put, for example, here the potential of 0, and of course on the other one 0 voltage part. Then I would put or assert a potential of 1 on the other conductor, I would establish the electromagnetic field, or electrostatic in this case, and once obtaining that, I will find out that we can find out the charge just by adding the charges on this conductor. I would have the positive charge, for example, and I have the voltage difference, or potential difference, the voltage 1 volt. So I would be able to calculate the capacity by dividing charge by voltage. Well, but that means that this vector of potentials is a special one. It has the structure of, if I group, if I make a good numbering of those points, so I first go through the points on the zero potential part, all the other points here, and then I group the points on the part with the potential of 1. So I would have a vector which has zeros and then ones over here. So I know the potential because I prescribe it. So now if I have a numerically sound case, I could find out the charges just by putting I can invert the matrix M. So if it's not singular and if it's not ill-conditioned, I can invert it and get the set of potentials tau. And at the moment, I can establish the values of all the potentials, tau 1 to tau m, all the charges, tau 1 to tau m, and once knowing the charges, I can find out for any point in the system, the potential and or field strength or anything that I need. This, for example, has one big advantage for this simple case. I need no housing, no case to close the structure. You remember we had FDTD and we have been talking a lot of time about how to find a wall that does not reflect the wave back, how to simulate open space within a finite grid, because the finite difference time domain needs a grid that is, it handles open space with difficulties. This method only considers places where charges are sitting. The other places are not important at the time of calculation. So this is a method for open problems. In fact, I have calculated a number of structures with this method, still not knowing what kind of method it is. I knew it works, and I even had a presentation on a small conference, and still the people there who have been working in electromagnetics gave me no hint. And only later I found out that in fact it's a kind of a method that is called a method of moments. We have a green function that tells you the result of a source that is the charge, and we have somehow tested it. Now this is a fast method, easy to write the code. It can handle some problems. My estimation is that you can go up to 250 points, 250 wires without difficulties in most cases. If you increase the number of wires, the matrix becomes ill-conditioned, inverting it becomes difficult, and the results are not stable and not useful. I just wanted to show you this method as a first part of this lecture. It is in fact a kind of a moment method that will be given you rigorously by my colleague Miroslav Čapek next week on Tuesday after Easter. And I have just shown you a method that is of that kind, and you do not need any knowledge of all the method of moments, terminology and ideas. Just a short illustration that could possibly help you to understand the mathematical backgrounds of the method of moments. Now I will stop with this with a question for your questions. Are there any questions from your side? Is it understandable?
I think yes.
Well then, okay, so then we will switch the topics. And as I have used the last paper in one of my flip charts, I will make a 5 minutes break to supply more paper, and then we will switch the topic to optimization. So please, 5 minutes break.